So today we are basically at the last theory lesson. After this, I'm just going to give, a quick guide as to if you want to continue learning about machine learning, what can you do next? But this last theory bit is about transfer learning. Again, we're on Kaggle. We're going to talk about, here you see an outline. We're going to talk about what transfer learning is, what it's good for, how it works, how you can apply it, and that is it. So the first thing, when it comes to transfer learning, it's kind of like you're transferring other people's work into your own. So, in other words, plagiarism learning, but in machine learning community, we call it transfer learning, but yeah, it's plagiarism learning. Um, the reason why we do plagiarism learning, it's because we are doing good for the world, okay? If anyone ever asks you, why are you plagiarizing? You say, I'm doing good for the world. I will show you an example. So on the interwebs, you will see a lot of images like this, where you might have some accompanying text over yonder and hither, and there might be, memes galore times a billion when it comes to images of cats on the internet. So if you wanted to train, an image classifier of cats, then you're in great luck. You can find billions of sets of training data. You can find, grainier versions of memes until you have all the data variety you would want. But let's say you want to do good for the world, okay? Let's say you want to look at, say, a CT scan, a cardiography scan, and you want to be able to diagnose, say, like a tumor in the head, maybe some kind of abnormality in the spine. Now, these types of radiography images, healthcare images, these are a lot less common. So it seems like the world is against us. If we want to look at how to identify memes, then we're good. But when it comes to doing real good, then we're quite limited. This is like a big problem that many people have to deal with because, it's expensive to get data like this. Whereas you can find this on the image anywhere, in the internet. Over here, you might have to, get around confidentiality restrictions. You might have to pay hundreds of dollars to do each scan. You have to find all these humans who are willing to get over the privacy risks and, send their head images to you. So it's quite a hassle sometimes in machine learning to be able to do good, just because of data restrictions. This is originally why we came up with transfer learning. It wasn't about plagiarism or, minimizing efforts. It was a good idea. They thought, well, we're training all of these algorithms, say, for example, neural nets, to classify images like these into cats, dogs, whatever. And not just cats, dogs, but like thousands of different things, like, human heads or bicycles or, shop signs. So they thought, if we're creating these models for all of these common types of images that we have, all these common types of objects that we have a lot of images for, surely like some parts of what those models learn can also be useful for a task like, let's say, identifying an abnormality in this poor fellow's spine. They thought, surely, like if we're training this model to create some kind of knowledge on this task, some of what it learns, some features, some activation somewhere in the model, some of those numbers could be useful even if we feed like an image like this into the algorithm. Now, I want to really make sure to emphasize the intuition here. So what the researchers thought was you have, let's say, for example, a neural network. Yeah, at some layer in the neural network, you have a series of activations, and those are just numbers. The researchers thought, well, it's kind of like those numbers. They're like a set of features that we can use. Just like we can use features that are like, real world data, here is the square footage of the house, here is the number of bedrooms and so on. They thought that the numbers generated by, some layer of a neural network, those were also like features. It's just that it's a little bit harder to understand, what those features represent. But at the end of the day, they're just numbers. So they got an idea. Just like we use features and feed them into neural networks to classify things in, say, regression data sets, why can't we do that for these activations of a neural network? So those features, like we generated, these features, some AI algorithm generated. So why can't we take AI algorithm A, take the features that it generates, and pass them into AI algorithm B, where AI algorithm A might be, meant to classify images of cats and dogs and zebras, whatever, and AI algorithm B might be meant to classify, is there an abnormality in someone's spine? So we're using this data, running it through a model that's trained on data like this, and then the activations we get from this model, then we can feed it into a second model that will predict, okay, for this data, here's the information I want. Is this making sense? Do you have any questions? I'll show you some diagrams so that maybe less verbally, you can see more visually. Here, I'll show you this diagram. Hopefully that's somewhat big enough. So you can see over here, we have a large data set like ImageNet. It has millions of images for thousands of examples. And you can train a classification model on this large data set. So it's used to classifying like dogs, shop signs, cars, pedestrians, all sorts of things, including some things related to human heads. So maybe like it's used to classifying pedestrians. So some parts of like this classification model, it will need to be able to recognize, oh yeah, there is a head here. Usually heads have this shape. And if, spine is messed up, then there might be a little bit of a difference. Maybe the head shape is abnormal. So this model on the left, it's trained for labels, Ys, from this ImageNet dataset, which does not have any images that are, radiography scans. But what we do is when we have, this large amount of data, then we can train in this context, this first model. And then, we get some features from this, some set of activations at some layer of this classification model. And we can use those as input features to a new model that we have. So now in this case, we have like the target data. So this is the actual data we want. We will create a new model. This is saying something different. So I will explain why it's different in just a second, but just pretend it says new model here. I'll explain why it's different. But we will create a new model with new layers that predicts, the target that we want. Is this making sense? Okay, so why does it say something different? Let me explain that. So what it says here is that you take the old model with new output layers. Let me show you a different diagram that explains why this is the case. So when we take, some set of inputs and then a few layers from, this first classification model, and then, at the end, you would have some number of, output neurons, like one per class. So maybe like this one was just predicting, is there a cat or not? So maybe there was one output neuron for, is there a cat or not? What we do is we kind of like delete that output. We just keep, these activations that were generated by the model, because it was like the model could use these activations to predict there was a cat or not. So, maybe these activations that the model generated, maybe this knowledge we could transfer over to a second, neural network of ours. So when we think about what's happening, it's kind of like we delete the output layer of the first model, And then, we take the activations generated right before that allowed the first model to predict that output. And it's kind of like we, attach those weights and biases. It's like we attach those weights and, it's like we attach those activations to these new layers. So technically, like we're training a new model, but oftentimes the way that we explain this is like we're adding on new layers on top of the last model, where all of the weights and biases of the old model layers, those have been trained. So it's kind of like you just, put in the input image pixels, you'll get out a useful activation at the end here. And that's treated as like the input features to these new layers where we train the weights and biases. Is this making sense? Do you have any questions, Aditya?
So with back propagation, would you train the the old model and the new additions, or just the new addition part?
Yeah. So all of these like weights and biases, the researchers would have trained, wherever we got this model from, they would have trained. And usually we just keep these in place and we train, these new parameters.
My other question is, since like the neural network, you can't like decode what's happening inside of it. It's like a black box nature. So how would
Yeah.
you know one model has a relation with another model? So you can transfer learn it. How would you
Yeah.
know if that is related to a spine or something?
Yeah. So usually people would try to, take a cat classifier and then use it for radiography scans. They'd get bad results. The best answer is it's done empirically, meaning people just test out, different models, and people try and find standard models that some researchers have created on some data sets that seem to be transferable to a lot of contexts. So for example, the ImageNet datasets, because the models created for it, they're meant to predict thousands of different types of objects, including probably like some pedestrians in there, not just, cats, but probably something resembling some part of a human. Then they found empirically, just testing these things out and playing around, they found that that type of model has some useful information that we can use for a transfer learning model, say for radiology scans. But you could try to do, hey, cat classifier, does this work? Does this have useful information? Will it, work for my radiology classification? Oftentimes you might find that it doesn't. So it's that empirical, testing that has been done a lot. Does that answer your question?
Yeah.
All right. So hopefully some of that theory behind, why transfer learning models were created makes sense. I just want to let you know one last benefit to transfer learning, which is that, hey, we don't have to choose, much of a model architecture. It's done for us. We don't have to adjust hyperparameters much. It's done for us. We don't have to train and waste a lot of computational resources. It's done for us. So this original, idea of creating transfer learning just to get around those data issues now gets to make our life a lot easier. So let's just dive into it. How do we import, how do we use these transfer learning models? And keep in mind these benefits, less computation, um, less data. You can still, get out some pretty good results if you're in one of those cases, and then less trying to adjust architectures, hyperparameters, and so on. So I have this magic site for you. You can find common pre-trained examples, like common pre-trained models within PyTorch. So for example, for computer vision tasks, there are all of these models. like AlexNet, VGG, ResNet, so on. These are basically things that, people have created over the years, researchers especially, that have certain properties. They're kind of like standard case studies that other researchers or anyone making an AI model can reuse. And for example, if I click on AlexNet here, you'll see that it comes from a research paper in 2014. It's a specific type of convolutional neural network, CNN, which is basically an extension of a neural network. It has some advanced features that are useful for computer vision, but I won't explain how they work. And you can see here the benefit of AlexNet is it works very well when you have multiple GPUs. So those are like graphical processing units in your computer. So it has, very nice performance when you have many of these different computing tools. You could do a similar thing for all of the other models. You could see, this is why they were created. This is, the unique benefit they have. And any of these, you can literally import in, well, one line of code from PyTorch. So for today, I'm going to go with VGG. It's an older standard model, I will say. However, it's pretty simple. It works on regular images that you might have seen on the interwebs. So I'll be using that. Of course, common thing is you don't understand how it works because you haven't gotten into computer vision. So just think about the theory part and not too much, how it works. I just want to show you how you might use transfer learning. Keep in mind that for regular neural networks, logistic regression, transfer learning is less common than, say, for computer vision, natural language processing, some other more hard, more difficult tasks. Cool? So when you want to use any of these common, transfer learning models, you can just find them on PyTorch. I will send a link. Arjun, question?
Would how these models are trained matter? So let's say the VGG model is trained on a random data set, and we want to do it on like another totally different use case problem. Would we still be able to do the transfer learning?
It depends. So if the data set is like ImageNet, and it's just a bunch of images, including head-like images, and the transfer learning task is we're looking at heads, then yeah, it would be pretty good. If the model is trained to detect cars and figure out, so this is a stop sign, this is a road, this is a pedestrian, then maybe not.
How do we know if it's trained in a way that we want it to, and if it's not trained in a way that we don't want it to?
It's trained in the standard way that the researchers would have trained it in the research paper. So we have to rely on that to figure out, what the training was, and PyTorch just replicates it in like a PyTorch accessible format.
Okay.
Yeah, good question. So you'll have to read those research papers if you want to know the details, or search up more about these models online. These standard models, standard case studies, so that you can find out more details about how they were trained, how they were used. One more note on how to find them. So those are like the most common models that you probably need. You can find them, I'll link to this notebook, but you can find them within PyTorch itself. Other common models you can find in this useful site called modelzoo.co. You can find models for not just PyTorch, but TensorFlow, that's another deep learning framework. Keras, Caffe, that's like a C++ framework. It doesn't use Python, but you can search through, you can see quite a lot of models. So there's a lot to go through. That's another place that you might want to browse. If you click on any of these, They'll tell you, here's the use case, here's how you get started, here's how it works, here's how you import it. So that's a pretty useful site. And the last thing is you can literally just search up research papers. So for example, recently I was working on a mental health problem. I found this research paper by these authors, and they basically used mental health reflections and turned it into motifs like images, icons to decorate some, chats or something. Um, but I was interested in the data, so they were nice enough to leave the data somewhere in here, and I was able to use that. But also, they had a data set of like 1,500 text samples, so I was able to use that. But also sometimes maybe you're interested in the actual model. So this model, it had a natural language processing part to get from the words to some numbers, and then I also had the image generation model. So you can look into, different researchers' work and like see what they're using, see how they're using it, and so on and so on. So those are three different, ways to find models. But really it's just one way repackaged. Usually they come from machine learning researchers. Make sense? So if it's built into PyTorch, if it's that common, easy time. With Model Zoo, a little bit harder. You'll have to learn some irritating stuff. And then with the research papers yourself, well, yeah, you're kind of copying code. So plagiarize. Hopefully, you've built up your plagiarism skills in school. But yeah, you got to deal with that. Anyways, that's how we find models. Let's get into how we actually use these models. So as you can see, let's say we're using, Vgg16 from PyTorch. It's literally built into Torch Vision. So Vgg16, we can literally import it, torchvision.models.that number. One thing that we can do, so you'll have to like look up the custom docs for each model to figure out, what are the arguments that you can use. In this case, I can just pass in the number of classes that I want as an output. So, how many of these output things do I want? And it'll automatically, delete the number of outputs it has. By default for VGG, it's 1,000. I know that because of, the documentation on it. And I could, put in 2 or 3 or 5 or 6. And just for demo purposes, I'm going to be using this dataset, Intel image classification. It basically lets you classify images of buildings, forests, glaciers, mountains, seas, and streets. So 6 classes. That's why I'll link to this dataset in the description, but that's why I put in 6 over here. Cool. So that's how we import in the model. And in this case, when I'm importing this, it's just going to import all of the neurons and, all the architecture, all the wiring. It won't import in the weights and biases. I haven't told it to do that yet. So this first type of transfer learning, what we're going to do is we're going to attempt to train all the weights and biases ourselves. We can do that. And the benefit of a transfer learning model like that would be that, you already get an architecture that works, that's been texted, number of layers, number of neurons per layer, but you don't get the weights and biases. You might want to do that because it might give you like more, let's say, customized performance for your own model, but likely you don't need to these days. I'll show you anyways if you want to. So you can just import this like this, and it returns a class that is like a full-on model. It has a forward method and everything, just like the classes of models we've been creating. I did want to show you the Vgg16 architecture. That's what this is called. So, what is the dimension of the input? 224 by 224 by 3. So 224 pixels high by 224 pixels wide. And this 3 refers to what are called channels in computer vision, RGB, if you've ever heard RGB values, red, green, and blue. So each pixel has like 3 numbers that tell you, oh yeah, increase the red levels a bit, increase the green levels a bit, increase the blue levels a lot. So before, in the last lesson, we used the MNIST dataset where it was black and white. We only needed, one number, make it more black or, less black. However, in this case, we need 3 numbers, R, G, and B, red, green, and blue, to be able to get a colored picture. Make sense? In the middle, you have a bunch of stuff that you don't need to worry about. You have these things called convolutional layers, max pooling, da 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 da. Who cares? All that we care about is we get to plagiarize. So if if you are ever learning about computer vision, you'll know what is going on right here. But if not, just know 224 by 2, like you need a image that is a square and it has to be RGB encoded. And then you get back an output that is 1 by 1 by 1000, typically. In our case, we just delete those 1000 neurons at the end and just, put in 6 classes instead. Make sense? So what I'm going to do now is I'm going to just grab some test data. Here's another way that you might see these models represented. This one just shows, the different layers involved. By the way, these fully connected at the end and these dense layers, they just basically mean neural network layers, like standard neural network layers, the ones that you're used to. This other stuff you can learn about if you're interested in computer vision. So anyways, once you figure out what the architecture is, what the input is, what are the expectations, you can even, look at the source code of these models. For PyTorch, like literally they will give you the source code. It's a really long file. You might have to do some reading to figure out, what's going on. Luckily for you, I did that. One thing to note. So we're using Vgg16, which is, because it has 16 layers. One thing to note, look, the required minimum input size of the model is 32 by 32. So we need at least a 32 by 32 image, otherwise it won't work. So sometimes you do want to check out like the source code to see what's going on. Anyways, let's just train the model. So we imported the model, replaced the 1000 outputs at the end with just 6. When it comes to training the model, I'm quickly pre-processing the data that I was using, the Intel images classification, using torchvision.transforms. You don't need to worry too much about it. It's just data processing. You can learn about it if you're interested in computer vision, but I'm just cropping the images to be 100 by 100 pixels because that's at least 32 by 32. I'm converting the images to tensor values and making sure that they're float tensors, not, 0 to 255 values, those integers. Finally, I'm normalizing the values. I hope you remember normalization from a few lessons back when we did regression. The way that I got these random numbers, I read the docs that I just showed you, the source code, etc., and it showed me, make sure you normalize your values like this. So that's just something I did. When loading the data set, I used this PyTorch class called image folder, where you see like I have an image folder over here. I can just set the path to the image folder and it'll automatically, get all of the 2191 images in this folder and label them as buildings. And then same here, 2404 images here and label them as glaciers and so on and so on. So it just simplifies that for me. I just need to, set the folder path and tell it what processing do I want to do on the image data. So I want to crop it, convert it, and normalize it. And then finally, I'm just creating a data loader. You've seen this before. It just batches the data, breaks it up into batches of, for example, 32. In this case, I didn't set a batch size. I could if I wanted, but in this case, it's just breaking it up into batches of 1 by default. Hopefully not too concerning. It's not the main focus, just data processing there. Here we're creating an optimization loop. You've already seen this code before. Just note here. So Vgg16, it has a dot parameters list. We have that method, just like for any other PyTorch model, because it's a child of torch.nn.module. It's already got those parameters. So in the optimization algorithm, we pass in these parameters instead of our model parameters, and then the rest, So what we're doing is creating predictions by forwarding in the input. We get a loss, cross entropy loss, backpropagation, update the parameters, zero out the gradients, and that's it. Just repeat. Gradient descent, you've seen it before. I can run this. Let's see. Let me actually run this line of code. Vgg16 is not defined, so let me define it. And there you are. You see it's training very slowly. So that's why we don't like training. By the way, each dot here that you see, that's like one image that is processing. So you can see like how computationally intensive it can be to train, large models like this. That's why we don't like, just importing the model architecture, but not the weights and biases that they trained. To import the weights and biases that they trained, I'm going to show you how to do that now. Any questions just at this section? So far what we've done is we just imported the model from PyTorch. They were nice enough to, implement it for PyTorch, implement it for us. We just process some data for now, just some test data. I'll link to it in the description. Just created a simple gradient descent. And we're optimizing all of these parameters for all of these layers. But we don't want to do that. What we want to do is we want to get, pre-trained parameters, pre-trained weights and biases. And the way that we do that, pretty simple. We just pass in a parameter that says pre-trained. So what I'm doing here, you can see it's downloading the weights and biases. It's 530 megabytes of weights and biases. That's a lot of, parameters that we don't have to train, thank God. So I just call it, same torchvision.models.vgg16. I can replace Vgg16 with whatever model I want to use. I set pre-trained equals to true so that it downloads the right data for us. This time, remember by default, it outputs 1000, classes. So this time what I did was after that, I created a custom model with source.nn.sequential. You've seen this in previous lessons, where I go from like 1000 inputs to 100 inputs, put in a ReLU, and from 100 inputs to 6, which is, the number of classes I had, a forest, glacier, building, so on and so on. And then, torch.sigmoid to get those between 0 and 1, just because it's a classification task. Make sense? So I'm gonna, put in the images here, get out 1000 activations, then put in a 1000 activations here, and get out 6 final output layer predictions. So this already done. Over here, I still have the same optimization algorithm. Notice this time though that I put in custom.parameters because I want to update the parameters of this custom model, not the Vgg16 model. I have the same kind of code, except here, when I pass in the input to Vgg16 pre-trained, what I just got here, then I get features, 1000 of them, that I can pass in as input to my custom model, and that's what generates the predictions. Then I just take the loss using the predictions, loss dot backwards. And when I'm stepping, remember again, I must updating customs parameters, not these parameters. So if I run this, you can see now the training is a lot faster. So that's how we can import in the model without having to, pre-train all of the weights and biases again. So Arjun, question?
Yeah, so in the top, when we define the Vgg 19 thing,
Yeah.
we say that we want to have 6 classes, but then in the,
Yep.
but then why do we have to do that? Because at the bottom, we already say in our custom variable, we say we want to output 6 classes.
So in this case, with the first model, we were just importing the architecture, but we weren't importing the weights and biases. Yeah, down here, we weren't, using a pre-trained model. So what we had to do was, you see this last step, it's 1 by 1000. That means there's 1000 outputs at the end. So when we tell it, num classes equals 6, it says, hey, you don't need like 1000 output neurons for 6 classes, you just need 6. So it kind of goes and it deletes, this 1000. And when it's done deleting somehow, it goes, there you go, it's done deleting now. It goes and puts in just 6 neurons in its place. The reason that we did that the first time is because we were planning on training, all of the weights and biases again, which we did over here in this loop. You can see we said, hey, optimizer, train all of the parameters in this model. Now, the second time, when we got the pre-trained model, we were actually just training these last 2 layers, the custom layers that we kind of appended to the end. And because of that, here, now we, can put in whatever architecture we want. Does that make sense?
Yep.
So in this case, because we didn't put in the number of parameters, the number of classes, it just defaults to 1000, which is what Vgg16 architecture is. And then we just kind of imagine this is just like a feed forward function. We don't mess with it. We don't change the parameters at all. We're just using it to get some features. And then it's our custom model, that's actually training based on those features. Make sense?
Yep.
All right. That is it for, transfer learning. After this, we'd graph results, change hyperparameters, check for bias and variance. However, of course, if we have fewer hyperparameters to tune, we don't have to mess around with the architecture as much. Maybe, just this end custom bits we can mess around with. So this is just like a random example with computer vision, but transfer learning is everywhere. It makes our lives easier. It's technically plagiarism, but no, it's not. Okay, we're making the world a better place. So I hope you like. I hope you will use. I hope you will not misuse.